Okay, so how is everyone today? Good, I hope. All right. So last time we were talking about solving inequalities. We're going to do a little bit more of that and then move on to an entirely new topic. So here's a little hidden block that if this were a graded exercise, you wouldn't see it. I'll choose two numbers. How about -4 and +7? From these, I'll make a quadratic. I'll make a nice quadratic. Then what? Multiply it out and collect like terms. So x squared minus 3x minus 28. Then I'll make another selection of just any old degree 1 polynomial, and I'll add these two things together. Again, this is just me making an exercise. If I add those together, then I get x squared plus 2x minus 26. And then here's the exercise. Please solve x squared plus 2x minus 26 less than 5x plus 2, and then I'll say specifically with a sign chart. All right. So that means that, in the first place, this is a nonlinear inequality, but we don't even need to worry about any of that because, well, the only consideration in which that matters is whether or not we're going to use a sign chart, but the instructions say to use a sign chart. What's the first step in this sign chart method? Natural domain. Okay, and for this inequality, what's the natural domain? All reals, right? Because remember that the only ways the natural domain could be restricted are divisions by 0, and there's no divisions, or negative inputs to even radicals, but there are no radicals of any kind. Therefore, the natural domain is all the reals. Notably, I want to make sure that we have two words, and often it can happen that students are think that they're synonyms or otherwise don't understand the distinction. Given an inequality, there is something called its natural domain, and there is another something called its solution. So the natural domain is the set of all things that are permissible to plug in, without regard to whether or not, when you plug it in, the result is true. So we're saying that, in principle, you could plug anything in. What's the solution? When the logical value is true. The solution is a subset of the natural domain. The solution is, of all the things that are permissible to plug in, the solution is the set of all things that, when you plug them in, the evaluation is true. Okay. 2. The next step in the sign chart method is to 0 and simplify. So what does the 0 part mean that we need to do? So here's I'm just copying it. So there's like two aspects to this step. What is the 0 aspect? What is it we're supposed to do? Get it? Very good. Get everything on one side. When you get everything on one side, then 0 is left on the other side. which is why I chose to name it the 0 step. Okay, so I got the 5x over there. Now I'll get the 2 over there. Leaving a 0 on that side. So the 0 part of it is done. Then for simplify, this, what is the specific kind of simplification that we're after? We want to factor it. So does this factor? Yeah. I know that it can feel a little bit silly, right, that I literally have the factorization written right there. But I'm telling you that this is all that I'm doing. Like when I make an exercise, like I do exactly this, and then I just don't show you that part. Fine. So now, well, the reason why we want to 0 one side of the inequality is because inequalities are a little bit slippery in that when you want to perform operations on them, for example, if you want to multiply both sides by something and preserve the logical value, you have to remember to reverse the direction of the inequality. And that's like a, you know, that's like a tool, in a sense, that's too dangerous to use, right? So a chainsaw, that's something that someone can reasonably be trained to use safely and cut down a tree. It is also the case that you could cut down a tree with, I don't know, like a 5 megawatt laser. That would work too, but in principle that's probably too dangerous for the average person. So we move everything to one side so that we don't have to do any of that at all. Then we factor it. Why do we want to factor it? In the first place, it helps us solve the equation, surely, but also by the time we get to the sign chart, right, what do? We want to plug values into these individual factors and check them for sign. That's why we want it factored. Okay. 3. So we want to solve the equation. So we'll take exactly that inequality. So I'll write exactly the left-hand side, and I'll write exactly 0, which is the right-hand side, except instead of writing the inequality symbol, whatever it is, we're going to write equal. So it doesn't matter what this was in this step. Less than or equal, greater than or equal. It makes no difference. We're going to write equal, and then we're going to solve this equation. Because we did all the work up here, this is straightforward. So the solutions are -4 and 7. This whole method is named after step 4. Step 4 is making the actual chart, the sign chart. So you plot the reals, and we're going to plot several fence posts, several marks here. In this specific exercise, what are we going to plot? -4 and 7. And in this specific exercise, both -4 and 7 came from step 3, solutions to the equation. Is it the case that all of these fence posts on all exercise will always come from step 3? No, because where else could they come from? They could come from step 1. If we had needed to exclude something from the natural domain, then that would also need to be marked. All right? So now in each region, I'll select a point. I'll select -5 for the left region, 6 for the middle region, and 8 for the right region. And then we're going to plug those values into what? This one, right? The inequality. And the reason why I want to stress the difference is not to be difficult, but rather sometimes when you solve the equation, you'll write several steps. We didn't have any steps here because it was kind of straightforward. But there could be several steps, and if you plug it into the equation, one of those steps may have changed it. So it's got to be this one. This is the one that controls the answer. So plugging -5 into those two factors, the left factor is negative and the right factor is positive. No, they're both negative. What am I saying? So the sign pattern in the left region is negative, negative. In the middle region, the sign pattern is positive, negative. And in the right region, the sign pattern is positive, positive. Any question about finding the sign pattern? Okay. Then the overall sign, the product of two negatives is positive. The product of positive and negative is negative. And the product of positive and positive is positive. So now we've made a sign chart, which is to say that we took the entire domain, cut it into pieces, and then labeled each piece with either the label negative or the label positive. From that chart, we're now able to make a conclusion. In every sign chart method exercise, you want either all of the regions that are labeled negative, or you want all of the regions that are labeled positive. In this exercise, which one do we want? The negative ones. So we want the negative regions, but on different exercises it can be different. Why is it that in this exercise we want the negative regions?
Because we've said the inequality says less than 0.
Because it says less than 0. If we were to go back in time and change that to greater than 0, then the majority of the exercise would be exactly the same, except we would now want the positive regions. Okay. Fine. So, are there any negative regions? There are. So the last consideration to get the answer correct is you need to consider the boundary of the region that you're interested in. Here I see this middle region is one of the ones. -4 is the left boundary and 7 is the right boundary. And the question is do we include them or do we not? So how about 7? Is 7 part of the solution?
No, because it would make it 0. And it's got to be less than 0.
Right. In the end, again, this is the thing that controls the answer. Remember, an element, an x, is part of the solution if, in the first place, you can plug it into the inequality, and it's defined, and furthermore, its value is true. If you plug 7 in to that factor, then it's 0. It makes no difference what the other one is, because the product is 0. And then the last thing to ask is 0 less than 0. It is not. Therefore, 7 is not part of the solution. Similarly for -4. So we want everything between -4 and 7, but not -4 and not -7. So as an interval notation, you could write it like this. Then how could you plot it?
Open circles.
Yeah, open circle at -4, and then this line segment here. And then algebraically, that is to say with inequality symbols, you could write it as -4 less than x less than 7.
What if you wrote it like instead of wrote it equal to -3 equal to 6?
That is not fine. And the reason why it's not fine is because, to be clear, so this is a so here's a zoomed in version of it. Okay, so here's the value, I'll say, -3. So -3 is in there. 6 is in there. Is 6.1 in there? It is, right? It is in there. How about 6.9? It's in there. And 6.999, it's in there. 6.9, and there's 1,314 nines. It's in there. So in the end, well, I'm not like trying to mash you or something. I just want to point out that it's a common mistake to consider to think that the kind of thing that x is an integer. In fact, x is a real number. But the conceptual error was that you had considered tacitly that it was an integer. Other questions? Okay. So here's a different question. Consider the following plot. So that's the red one there is that parabola defined by that quadratic. And the green one is a line defined by this. These points, where they intersect, so that is the point 7, 37. And this is the point -4, -18. So in this style of exercise, this picture is the thing that I gave you, so it's provided. Now the instruction is.
The points are provided as well.
Yes, the points are provided. Well, I mean, one way or another, yeah. Yeah, I would probably give the points because otherwise, you'd have to get out a ruler or something. I lost track of what I was saying. Oh yeah, use the plot. Use the plot to solve x squared plus 2x minus 26 less than 5x plus 2. And I'd like to point out that this inequality is exactly the same inequality as the previous page. It's exactly the same one. But the instructions are different. On the previous page, it was solve this inequality with a sign chart. And on this page, it's here I've provided a plot to you, and I want you to use that plot to solve the inequality. Okay. So here we go. Here's the inequality. X squared plus 2x minus 26 less than 5x plus 2. Presumably from the instructions, somehow there's got to be a relationship between the plot and this inequality, right? Because otherwise, why would I, what would the instructions mean? They'd be nonsense. This quadratic concerning the plot, what item in the plot corresponds to this quadratic? The parabola. And concerning this linear polynomial, this degree 1 polynomial, what item in the plot corresponds to it? The line. Okay. Furthermore, so we have parabola. And we have line. Here's the last bit that you have to connect. Did you have a question?
I was going to make a guess.
Okay. What?
I was going to, I mean, just by looking at it, like, those values would be the values that are inside the red bottom portion below the green line.
Right. So in particular, we want the less than means that we want below. So to be clear, to translate this sort of, what I'm doing is I'm doing like a step-by-step translation of the inequality into English. So the final thing in English is that we want the x values such that the y value of the parabola, well, you could say it like this. Visually, the parabola is below the line, such that parabola below the line and then translating it to be as precise as possible. We want the x values such that the y value of the parabola is less than the y value of the line. So my last question before we finally write down the answer is that here we're talking about y values, and here I say less than. So why does below the word below translate to less than when you're talking about y values?
Because you're moving down the line.
Right. I think you have it. That is that the convention for bigger y values is going up, right? As a result, if we want points that are below, that if a red point is below a green point, that means that the red y value is less than the green y value, because the increasing direction is up. So, fine. This is all just sort of, really being overbearing. Where are the x values where the y values are, where the parabola is below?
That region below the green dependent parabola.
I make no dispute. I agree entirely. But I need you to tell me the x values.
Between negative 4 and 7.
Between -4 and 7. which writing it as a plot would be this way, and in algebraic notation this way, which is of course the same answer as the previous page. Now, there's two purposes to this exercise. One purpose is to show you that this inequality can be solved in two different ways. One of them is the sign chart way, and you might characterize that way as sort of, I'm going to solve it using algebra to the exclusion of any pictures. You could think of it like that. Then you have this plot way, and you could say, well, I'm going to solve it with pictures to the exclusion of any algebra. So I want you to know that there's kind of two ways to do it. Generally speaking, the more difficult a problem is, the more likely it is that you're going to have to use some combined strategy. Like, oh, for this part of the work, I'm going to need to do algebra. And for that part of the work, I need to do some pictures. That'd be really nice. Furthermore, when I ask, most students respond that this style of exercise is far easier. Well, that's probably true. But the reason, in the end, I want to make sure that you understand it. The reason why this is far easier is because human beings have a phenomenally advanced visual system. And if I give you visual data, you're able to reckon things about it and summarize things about it very quickly. That's just, humans are just that way. But I could ask the same answer of children. Okay, so it's not that way. It's not that complicated. The purpose is I need you to know that when you're prompted with such an inequality and a picture, that, well, oh, I see. This quadratic corresponds to the parabola. That line that linear polynomial corresponds to that line. Now I could give you a picture with like two parabolas, right? And you can imagine in your mind's eye the way two parabolas could intersect. And then you'd have to ask yourself, okay, the inequality is saying that there's the red parabola and there's the green parabola, and the inequality is saying is I want to know everywhere that the green parabola is above the red parabola, or what have you. Good. So just the correspondence. Any question about this? Yes?
To get more used to doing it the sign chart way, is it better to practice alternating, like do one problem this way, the next problem the sign chart way, and keep alternating that way so you don't get stuck?
Right. You definitely need to do both. If for no other reason that I will explicitly say do it with a sign chart or do it with a plot. If for no other reason than that. But really there's a better reason. There's two better reasons. One is that if you understand both ways, then you probably understand the topic better. Furthermore, my experience in teaching, and also just generally, is that for most problems, especially math problems, each individual is very likely to either understand it primarily in an algebraic way or primarily in a picture way. And my experience, furthermore, is that it's about half and half. So odds are that when you talk to someone, about 50% chance that they think of it the other way than you. And if you want to communicate with them effectively, then you've got to be able to say, okay, well, you like it with a picture. Let's look at it with a picture.
I have a question about it. So I think the thing I would think is, if you gave us the inequality and not a picture, I would be hesitant to use a picture.
Yeah?
Because I would be afraid that there would be, because I can imagine multiple situations where like if you're doing two parabolas, where the parabolas don't intersect at all.
In a nice place, or even at all. Yeah, it can happen. Yeah.
Right. So I think my question then is how do I recognize that? I mean, unless it gets into too much detail, we can talk about it offline. But how would I recognize that?
In this class, it'll say, use the plot, and the plot will be given. So in this class, that's sort of an easy answer. But
I don't have to worry about it.
right, and then generally speaking, out in the wild, in the real world, in the first place, I have difficulty imagining where this would come up. But if it did come up, as a first guess, like if I was doing it, I just plot it immediately. I just plot it and just have a look, and to give me a general idea of what the case is in the real world. Yes. We want the x values such that the y value of the parabola is less than the y value of the line.
Do we get that from the diagram of the plot? How do we calculate the values? How do we find out the values?
Well, because from this intersection, that means that at this point, this is exactly x equal to -4. Everything on that line is x equal to -4. And this one, everything on this line is x equal to 7. So that means that if you're to the left of this one, you're less than -4. If you're in here, you're between -4 and 7. If you're over here, you're more than x is more than 7. But then the y value, notice that we didn't actually use -18 or 37. Those are, in a sense, just extra data. But those are always included in exercises such as this to see if the student's going to try and use them anyway. Right? Okay. The only thing that is necessary to answer the question is to know that the standard convention for y values is that the increasing direction is up. So we want to say it yet another way. We want the x values such that the y values, the red y values are less than the green y values. And that means below.
So we can mention this answer in y form too, right? Like if the y format, this is in the x format.
Well, no, you have to answer in x's, and the reason why you have to answer in x's is because the question was phrased in x's. Yeah. Other questions? Okay, good. So now we move to something entirely different. Good. So now we're in chapter 3, which is called functions. And we're in section 3.1, which is called functions. And I want to give you sort of a bird's eye view of what's happened so far. So, so far this semester, we've talked about the following kinds of things. We've talked about arithmetic a little bit. We reviewed that at the beginning. Then we reviewed some algebraic rules like FOIL and the rules of exponents and things like that. Fond memories. Then we talked about expressions. And then given expressions, we talked about their natural domains. And then once we were comfortable with expressions in their natural domains and we included radicals and things like that, then we said, oh, there's such a thing as an equation. And then we took some time to define what a solution to an equation is. And we also talked about the natural domain of an equation and their solutions. We talked about graphs, made a few plots, nice things. Then we talked about inequalities, their natural domains of inequalities, solutions to inequalities. Great. So sort of a short list of items that we know are the kinds of things that we know are expressions, equations, inequalities. And they all have a natural domain. We're going to add another one to that list, and it's called functions. So now we have yet another thing. So now the way the book is organized is chapter 2 covers all those things that we just said, but it does it really pretty superficially. That is to say that the book in chapter 2 talks about inequalities, for example, but it only talks about linear ones and absolute value ones. It doesn't talk about nonlinear inequalities, but we did. And the book talks about expressions, but it doesn't talk about the natural domains of expressions. It just doesn't talk about that. Rather, the author takes the strategy of that we're going to introduce these topics and do them sort of lightly. And then in Chapter 3, we're going to introduce functions, and we're going to revisit all those Chapter 2 topics in the light of functions. But the coverage is still going to be a little bit light. And then in Chapter 4, we review it all again, and now kind of get into things more significantly. But I find that that strategy doesn't work because you know, if students aren't good at the items introduced in Chapter 2, then it's meaningless to go on to Chapter 3. In the same sense that if you ever find yourself teaching and a student has a question, or you suspect a student has a question, you should stop and answer their question. Don't keep going. And the reason is because if you don't answer their question, they're not listening. They're confused and stuck at that one point where they had a question. So, that being the case, I want you to know that our experience of Chapter 3 is going to be like, okay, we're going to define a function, and then it's going to be more or less like, you remember that thing we talked about in Chapter 2? Let's talk about it just a little bit more, but in the context of functions. And there's not going to be a lot to say, because we already really digested that topic. So you're going to have the sensation, I suspect, of us moving quite along quickly, just saying, you know, expressions with functions, equations with functions, functions and domain, blah, blah. Yes?
Are functions the more applicable part of algebra as far as the real world accounting?
Yeah, I mean, they're well, I'll say it this way. Functions are the central objects of study in math. And math is like the probably reasonable to say the queen of all the sciences because it is so important. I don't know, you know. Maybe physics, I don't know. Because in the end, you know, you could argue that math is not a science. It's in the School of Natural Sciences and Math at UTD, but like, for example, at a school like Harvard, the math department is in the Arts and Humanities School. Whatever. It doesn't matter. Good. So here's the first definition. A relation is a mapping from one set, from a non-empty set D, which we will call domain, to a non-empty set R, which we'll call the range. Okay, so for example, I'll represent set D as just this box with stuff in it. So how about 1, -3, and smiley face. The only reason why I put smiley face in there is just so you don't be misled and think that we can only talk about numbers. That's not the case. So here's the range. I don't know. 6, 7, 10, and 2. Okay, so then we have a non-empty set D and a non-empty set R, but we don't have a mapping, whatever that means. And in this case, the way we're going to do mapping is I'm going to draw arrows from items in D to items in R. So 1 to 10. So the way that you say that is that 1 maps to 10. You could also say 1 is related to 10. And I'll say that 1 is also related to 6.
Are you doing this arbitrarily?
Yeah, I'm just doing it. Then I'll say -3 is related to 7. And then smiley face is really gregarious, so it's related to everything. Well, I guess except 2, because 2's maybe a loner. I don't know. Okay, such a thing is called a relation. So again, you could say 1 maps to 6 and 1 maps to 10. -3 maps to 7, etc. And you can ask questions a different way. You could say, for example, what maps to 6? 1 in smiley face. What maps to 2? Nothing maps to 2. Okay, so we're not really going to talk a lot about relations in our class. What we're going to talk about is functions, and a function is a specific kind of relation. But that doesn't, I would encourage you not to just think that this is just something we're saying in passing, but I want to emphasize that relations are of extreme importance. An example would be something like, at the present time, 2 of the companies that are most known by the public and also very highly capitalized literally make their money by maintaining a relation. They calculate and curate and otherwise maintain an enormous relation. So the two companies I'm talking about that I have in mind are Facebook and Google. Right? Facebook maintains the relation of who is friends with who. And they maintain that publicly. Privately, they also maintain that, well, I know that you're not friends with that individual, but I do know that you click on their posts all the time. So you're interested in them for some reason. So Facebook calculates this enormous relation, and that's extremely valuable to advertisers. So in particular, if you were not already aware, I'd like for you to become aware that you are not Facebook's customer. You are Facebook's product. Part of it. Advertisers are Facebook's customer. Similar for Google. Okay. That being said, we're not interested in relations. We're actually interested in functions. A function is a relation such that every element in the domain, so that means on the left side, maps to exactly 1 element in the range. So to say that in terms of arrows, that means that when you're looking at the left box, the domain box, it must be the case that exactly 1 arrow is leaving every element. So the question is, well, concerning this relation, is that relation a function? So how about -3? How many things is -3 related to? 1 thing. How many things is 1 related to? 2 things. How many are permissible?
1.
Exactly 1. So this one has exactly 1, but in order to be a function, all of them must have exactly 1. So do all of them have exactly 1? No. Okay, so it's not a function because, for example, 1 maps to 2 elements in the range. but the only permissible number of arrows leaving is 1. Okay. So how about this one? So here's the domain. 1, 2, 3. And the range will be the reason why 6 is afraid of 7.
Something 8, something else, right?
Because 7, 8, 9. That 7 is scary. Okay, so let's say that 1 is maps to 8. Let's say that 2 also maps to 8. And maybe 3 maps to 7. All right, so is this a function? Yes. But wait a second, what about 8?
It's in the range.
Yeah, exactly. Exactly the right response. The consideration of whether or not a relation is a function is a question about what's occurring in its domain. Is it the case that exactly 1 arrow leaves everything in the domain? Yes. So asking about occurrences in the range is literally nonsense. Okay, so yes. 1 arrow leaves. Every element in the domain. Okay. Some more definitions. Again, about counting. A function is called surjective and then in some places you'll see it said onto instead of, they'll use the word onto instead of the word surjective when every element in the range is mapped to at least once. So at least once. All right. So the question that I'm going to ask now is, well, considering this function that's at the top of the page, is it surjective? It's not. It is not surjective because why? Right. Because nothing maps to 9. Okay, the second definition. A function is called injective and if the source you're considering is instead using the word onto, then it's very likely that the source, that same source, will pronounce injective as 1-to-1. I have to say these things because at the present time the mathematical community is kind of undergoing a transition where onto and 1-to-1 are kind of the old way to say it, and surjective and injective are the new way to say it. When every element in the range is mapped to and now the key phrase is different at most once. So for surjective, the quantity permitted is at least 1. For injective, the quantity permitted is at most 1. So now I'll ask concerning that function at the top of the page, is that function at the top of the page injective? No. Why not? Because 2 elements map to 8. Finally, a function is called bijective when every element in the range is mapped to that's a good idea, but no, is mapped to so it's when both of these conditions are true. So they have to be mapped to at least once and also at most once, which means
At most once.
it means that it's permitted for everything can have one arrow pointing to it or 0. So one or
Is it not a injective?
this is not injective because 8 is in the how many things point to 9?
No.
None. So where injective is concerned, 0 is okay. How many things point to 7?
1.
1. Where injective is concerned, 1 is okay.
Yeah.
How many things point to 8?
2.
2. That's too many.
It's only 1 can.
At most 1.
Okay.
0 or 1. So 0 or 1, 1 or more. So if at least once and at most once, then exactly once. Which means that the reason for the word by doesn't mean 2, it means rather both. That means that it is surjective and also injective. Good. So then that's all the time that we have for today, but we'll continue it on Friday. Have a nice Wednesday.